Today we're going to be talking about pressure volume loops, baroreceptors or MAP, mean arterial pressure, and we're going to talk about capillaries. Let's get started. Okay, like I said, PV loops, pressure volume loops. We'll talk about the baroreceptor reflex and how that regulates MAP, mean arterial pressure. And then we'll also talk about capillaries and then give an example of edema. So we're going to start with pressure volume loops, also known as PV loops. So what we're looking at here is we've got pressure and volume, pressure for the Y, volume for the X. And then what we're looking at is just during a cardiac cycle, what is kind of happening here. So we'll start here in this corner, okay? I have it labeled MO, and that is thinking of the ventricle. We're talking about the left ventricle here. So MO stands for mitral open. So the mitral valve between the left atrium and the left ventricle is open. So there's a filling of the ventricle right here. If you can see that, the volume is increasing and the pressure is slightly increasing here. So this is just passive filling as the ventricle does. So at this point right here, mitral valve is open. Once we reach a certain pressure, our ventricle has more pressure than the atrium, and so the mitral valve closes. So right here in this spot. Okay, and so now at this point, both valves are closed. The mitral valve and the semilunar valve are closed. So now we just have isovolumetric contraction. Okay. Until we reach about this point, this graph isn't perfect, but this shows that at this point, our semilunar valve opens. So we've reached high enough pressure that we've blown open the door between the left ventricle and the aorta. So now, this period right here is called the ejection period, because everything that's in the ventricle is being pushed out into the aorta, okay, until the pressure in the aorta or the ventricle becomes less than what's in the aorta, and so then the semilunar valve closes. And so then respectively, this is lub, this is dub. It's when these valves are closed. The mitral valve is the lub-dub of lub-dub, and then the semilunar valve closing is the dub. So S1 and S2. Okay. So then once the semilunar valve closes, our ventricle starts to relax. At this point, both valves are closed again, just like they were on this side. And this is known as the period of isovolumetric relaxation. Okay. Also, you see here that I have EDV and ESV. If you'll remember from my last video where I was talking about the cardiac cycle, EDV is the end diastolic volume. So you'll see here it's about 120 milliliters during diastole when it's relaxed. The ventricle is relaxed, so it's not contracted, it's relaxed, it's filled up as much as it can be in its relaxed state to 120 milliliters. The ESV is once it's all contracted, the ventricle's completely contracted, then we're back down to about 50 milliliters. That's the end systolic volume. Inotropy, preload and afterload. The way that we look at these, inotropy is the stiffness or the contractility of the heart. So what we're dealing with in inotropy is the amount of calcium, right? Because calcium is always linked with muscle contraction, and the heart is just a great big muscle. Okay, so if we have more calcium, then we're going to have more stiffness, more contractility. If we have more stiffness or more contractility, then this line kind of right here is going to steepen, because we're going to have a shift here. And so now this is what our new PV loop would look like. Can you see how this is shifted over from where it was? That's because of increased contractility due to calcium in the heart. Okay, so it shifts this line up. This is the inotropic line. So what that means is when it's contracting, it's getting rid of more, right? And that makes sense. And I could even do more or something, right? But that makes sense to us, because if it's contracting even more than it was here, then we're going to get rid of more and more, right? And so it just shifts that inotropic line farther and farther and farther over. And that has to do with, again, the amount of calcium that's being released in the heart muscles. Okay? So now we're going to talk about preload, which is how much we can fit into the ventricle. So if we're dealing with just this normal one, then preload could go clear out here to maybe, I'll say 140 milliliters, right? And then everything else would be about the same. Okay, and this would deal with preload, which means our ventricle is stretching more, right? Inotropy had to do more with contractility, how much it's contracting. So it was getting more out. Preload it's filling up more. Can you see that difference? So that's how they're different. So inotropy deals more with elastance, where preload deals more with compliance. It's more easily filled up. Yeah. Anyways, hope that made sense. We're dealing with afterload. We're talking about how difficult it is for the heart to pump blood through the system. Okay. This is kind of harder to show, but if you think about it, it's not too hard to think about. It would increase this point to up here. So if the heart has to work harder, say we're vasoconstricted, or there's aortic stenosis, which means the aorta isn't as elastic, it's harder to stretch it, then the heart has to work harder to do that. And so because it has to work harder, it's not as easy for us to reach, or it takes more pressure to blow this door open, so it shifts up here, right? And so when it does that, the heart is now tired, and so it doesn't come as far over here, so it's going to have decreased contractility here. So we're going to have a higher ESV rather than what we had down here. And so that's how we understand inotropy, preload, and afterload. That's kind of the effects that they have on the PV loop. We're going to move on now to variables that regulate MAP. Specifically, we're going to be talking about baroreceptors. So I'm going to start here. I have it written out here, but I like drawings. Drawings seem to make more sense to me. So I'm going to start with this, and then I'll kind of reference that as well, if that makes more sense. So we're going to start by talking about baroreceptors. So a baroreceptor is basically a stretch receptor or a pressure receptor. So what it's doing is when the ventricle is pumping blood out into the aorta. Blood is coming up these carotid sinuses up here as well. And what they're doing, because this is elastic, is when blood comes up, this aorta stretches and it kind of stretches out, and then the same thing happens here. If this is happening too much, if it's stretching too much, we're going to have a signal that comes through and says, hey, we need to decrease our heart rate. There's too much blood coming through here, something could pop. So, or vice versa, if there's not very much blood coming through here, this will be like, hey, we're not stretching as much as we normally do. And these guys will sense the same thing. And so it'll say, hey, we need to increase our heart rate so that we have our regular amount of blood coming through here so that our tissues are getting what they need. Also, so we don't pass out. So what's happening here is we have these afferent or afferent nerves going from your carotid sinuses and from your aorta here. From your carotid sinuses, we have your glossopharyngeal nerve or your cranial nerve 9, and then your vagus nerve or cranial nerve 10 coming from the aorta. And then what they do is they come into your CNS, and then they're going to affect your PNS and your SNS, your parasympathetic nervous system and your sympathetic nervous system. The PNS is going to work again through the vagus nerve on the heart, and it's going to help us slow down our heart rate, or if we turn it off, it'll allow us to increase our heart rate. The SNS works in several different ways. It can either act straight on the heart through the beta, through its beta receptors, or it can come down to the adrenal medulla and increase epinephrine release, which will also cause an increase in heart rate. Or it'll act on the arterioles and it'll vasoconstrict the arterioles so that it causes higher blood pressure. So again, kind of looking at this over here, you have the carotid sinus and the aorta, cranial nerve 9, cranial nerve 10. It goes specifically to centers in the medulla, right? But then the effector organ is the vagus nerve. It's the PNS, and it affects the heart directly. Sympathetic fibers, you can go straight to the adrenal medulla, or you can affect the heart and the arterioles. But this kind of leads back to the heart and helps us control our blood pressure and everything. Our MAP. Our MAP equals or stands for mean arterial pressure. Okay. And that is equal to cardiac output times peripheral resistance. So if we increase our peripheral resistance, which would be vasoconstriction of our arterioles or vasodilation, that will help increase or decrease MAP, depending on what we need, MAP, depending on what we need. And then we can either stimulate the heart to go faster or slower, and that will affect our cardiac output, thus affecting our MAP. Okay, so a couple different ways we can affect MAP. Some other things we can talk about. I'm not going to spend lots of time on these, but they are MAP regulators. So a chemoreceptor, it responds to changes in oxygen, carbon dioxide, and hydrogen levels, so our pH. They're going to increase cardiac output. So it really senses a decrease in oxygen and an increase in carbon dioxide and I'm blanking on it, but an increase in pH. So when it senses this, when the chemoreceptors sense this, they kick our heart rate up so that we're pumping blood through our tissues, getting more oxygen to them, and it's also increasing the amount of blood we're pushing into the lungs so that we can get more oxygen. So it works twofold that way. The adrenal medullary mechanism is kind of like up here where we were talking. It increases epinephrine, which increases heart rate and causes vasoconstriction, which increases our blood pressure. This renin-angiotensin aldosterone mechanism has a ton of parts, kind of a big thing. So I just wanted to help you understand that there's several things it does that it increases blood pressure and thus helps us regulate our MAP. So that's kind of what we're talking about with MAP. These are some of the effectors for it. We're going to move on now to our final topic, which is capillaries. It's nothing too crazy. It looks like a lot, but I hope I can help you understand what's going on here. So what we've got going is we've got an arterial end, so arteries are coming in this direction, and then in the capillaries, our capillaries are only a single cell thick. So these are just one cell linked. I mean, it's one cell thick, I guess. So lots of cells connected, but they're only one cell thick. They're not, compounded on top of each other, right? So it's very easy for things to diffuse through or into, out or in. But what we have here is a precapillary sphincter, right? Because we want to be able to control how much is coming into our capillary so we don't blow our capillary open or apart, because obviously if it's only one cell thick, there's only so much pressure it can handle before it blows up, right? So that's why we have this precapillary sphincter, is to help us regulate how much blood is actually entering into the capillary. I guess I'll mention this. MAP that we were just talking about, above 160 millimeters of mercury, will blow out this sphincter, and so then it'll cause a whole bunch of hydrostatic pressure, which is also basically just blood pressure in here, and so it can cause issues. Anyway, so this precapillary sphincter is to help regulate the amount of pressure inside our capillary. Hydrostatic pressure at the arterial end, right here, is about 30 millimeters of mercury pushing out, right? So it's pushing fluid into the interstitium. This is I'll call this interstitium. Okay, so it's pushing fluid out into the interstitium just because there's so much pressure in here. So it's high pressure to low pressure, right? And so we've talked about gradients, and so it's a high to low. High to low is the common direction of gradients. So high pressure to low pressure, more fluid to less fluid, right? So that is out, and then we will have what's called BCOP, and it's blood colloid osmotic pressure. So what happens is here inside our capillary, we have all of these big proteins that are not able to diffuse across the membrane, right? But we learned early on in this semester that water follows solutes. So we have a whole bunch of this albumin. Albumin is the main protein found in plasma, in blood. And so it's pulling a whole bunch of water in here. And so we see that BCOP causes an influx of fluid. And it's about 28 millimeters of mercury of pressure in. And then ICOP is kind of the same thing. It's proteins in the interstitium. And so it has some big proteins that are pulling some fluid out. Okay? Doing the same thing, BCOP and ICOP, but it's a lot less for ICOP than it is for BCOP. But it is pulling some out. And then we also have IFP, which stands for interstitial fluid pressure, right? So as fluid builds up out here, these lymph vessels, these lymph ducts, they're pulling fluid up them, right, to help recycle this fluid and things that are in it. And so it's like a little vacuum that's just constantly going, so that fluid is constantly being pulled up in, and it has these little gates so that fluid doesn't leak back down into it, or it shouldn't. There can be issues where, this lymph vessel may be damaged, but if everything's working correctly, fluid should only be ever going up, never back down. Okay, and so that also causes a slight pressure out of the arterial end of the capillary. Okay, so when you add all of these up, out, in, out, out, we have about 13 millimeters of mercury of pressure out of the arterial end of the capillary. Okay, but then as we move through our capillary, it turns into the venous end of our capillary. And BCOP, it stays the same. Again, these proteins, they can't diffuse through the membrane, so they transfer over here. It's the same amount. So we're going to have the same pressure. So we're going to see 28 millimeters of mercury pulling fluid into the capillary here. However, as it moves from the arterial end to the venous end, our hydrostatic pressure decreases a lot, so that instead of 30, we're now dealing with only 10 millimeters of mercury. So it's not pushing out nearly as much, barely any, really. But then ICOP also stays the same. These proteins aren't able to diffuse across the membrane, so they also stay, and they're over here as well, right? This is all the same stuff. Okay, so it stays the same, so it's only pulling, so much fluid out at this end, and then the lymph nodes, they're constantly, or the lymph vessels are constantly pulling, so they're doing their thing as well. But because the blood pressure, the hydrostatic pressure is decreased so much, we now see that we have about 7 millimeters of mercury of pressure pulling fluid into the capillary, and then it exits the capillary and enters the venule, and it makes its way up to the right side of the heart. Right? So that's what's happening in the capillary. So I'm going to give you an example of edema, maybe two. So one thing that could happen is we could break open these tissue cells here, right? And if we break this open, there's going to be some spillage of proteins. Proteins are all over in these cells, right? So if we increase ICOP, then we're going to have more fluid from inside the capillary being pulled out, right? ICOP already has 8 millimeters of mercury pulling it out. So if we increase that to, 18, then instead of 13 out, we're going to have 23 out. And that's a lot more. And so that might even kind of overwhelm our lymph vessels, so they're not able to pull out that much fluid as fast as it needs. So we're going to have a buildup of fluid out here in the interstitium, and that is what is causing edema. Edema is a buildup of fluid, and so that's just one example. There's many examples here that we could talk about. All of these factors can be affected in some way to cause edema. But I hope all of this made sense to you. Thanks for watching and hanging in there with me. Have a great night.